Between 2023 and 2025, AI progress was measured in pixels and tokens. Models summarized text and generated code, but output remained behind a display. Development has now expanded into embodied AI, a field where neural networks directly control physical hardware to perform tasks in the real world. This flow matrix maps a complete architectural inversion. Digital AI processes data to generate information, while physical AI processes continuous sensory data into immediate mechanical action. A chatbot hallucination is low risk, but a processing error generating torque introduces severe kinetic risk. The core challenge for AI has moved from generating the correct text to maintaining safe, predictable movement within a three-dimensional physical space. Legacy automation relied on predictable, hard-coded scripts. A machine was programmed to move its arm to exact coordinates and execute a specific, repetitive task. Introduce a single dynamic variable, a spilled liquid on the floor or an animal walking through the workspace, and those scripts fail. The hardware cannot adapt to what it hasn't explicitly been programmed to expect. This limitation highlights the central engineering bottleneck in robotics, the sim-to-real gap. It is highly efficient to train a model in a frictionless, simulated digital environment. Transferring that intelligence into a physical world governed by gravity, friction, and unpredictable geometry is notoriously difficult. Bridging the sim-to-real gap is the mandatory prerequisite for any functional embodied AI framework. In unstructured environments, the primary danger is processing latency. The milliseconds it takes a model to compute its next physical move can result in a mechanical collision. To solve this, companies like Meta have developed architectures designed for real-world perception, seen recently in the release of Muse Spark. Muse Spark is natively multimodal. This means visual perception and logical reasoning are mathematically fused into the same neural network. Older systems relied on external vision plugins, translating image data into text before routing it to the processing center. That translation creates a delay that is unacceptable when routing commands to heavy moving mass. Because perception is native, the model can map human kinematics. Trained on data curated by over 1,000 physicians, it processes physiological reasoning on the fly, reading skeletal alignment and muscle activation directly from incoming video. Native multimodality is a safety requirement. Without it, the processing delays make physical operation hazardous. This decision tree illustrates thought compression. During training, the model thinks out loud, evaluating friction, weight, and distance across branching logic pathways. Then a length penalty mechanism is applied. The network is penalized for taking too many computational steps, forcing it to trim unnecessary logic. What remains is an optimized vector running directly from sensory input to physical execution. Standard language models output paragraphs of text over several seconds, but this compressed system executes microsecond physical reflexes. By punishing slow computation, thought compression translates high-level cognitive reasoning into fast, automated mechanical reactions. Operating safely in physical space also requires a machine to process several distinct analytical functions simultaneously. Systems address this through contemplating mode, dividing the cognitive load by spinning up specialized parallel subagents. Take a scenario where the AI is assisting a user with a yoga pose. The first subagent is a continuous vision process dedicated to mapping the structural alignment of the user's skeleton from the video feed. Simultaneously, a separate intelligence process evaluates that real-time skeletal data and formulates precise verbal corrections to guide the posture. Successful physical interaction demands this parallel orchestration. The system must perceive, analyze, and communicate concurrently rather than linearly. Beyond individual models, engineering focus has shifted towards standardizing how robots perceive their environments. The launch of the joint Fujitsu Carnegie Mellon Physical AI Research Center represents an investment in building universal software for robotics. They are developing the Kozuchi Physical OS, a universal brain designed to control different hardware chassis, from drones to humanoids. The OS divides processing into two streams: spatial intelligence, mapping where objects are, and brain intelligence, calculating how to move through that space. These systems bypass the need for task-by-task programming by relying on world models, internal simulations of physics encoded into the software. Because the software possesses a world model, a machine predicts that dropping a glass object will cause it to shatter upon impact. It calculates gravity and fragility without prior specific training on dropping a glass. Standardizing hardware through a universal OS separates the physical machine from its cognitive capability. This decoupling explains the recent increase in videos showing robots performing complex tasks, like navigating a crowded subway station or folding laundry. The driver behind this acceleration is the deployment of open behavior models. Much like open-source developers' shared text models, researchers are now releasing downloadable weights for kinetic movements. Startups can import these open-source physical behaviors, bypassing years of expensive physics training, and deploy fluid routines. This creates a hardware shift toward general-purpose robots as an industry standard. The logistics and healthcare sectors are adopting these platforms to fill unstructured, dull, and dangerous roles that legacy automation couldn't handle. The availability of these shared movement libraries means that for sectors like logistics, the barrier to deploying automated labor is no longer custom programming, but the cost of the hardware itself. As these natively multimodal systems mature, deploying them into domestic spaces introduces one final engineering limitation. When models act as a personal superintelligence, they require continuous perception of a home environment. At that point, the core challenge moves from intelligence to data security. The new engineering frontier is localized processing. The hardware must compute massive sensory inputs locally, operating through strict on-device privacy constraints. Continuously uploading a high-fidelity video feed of a user's life to a cloud server is a security danger and a bandwidth impossibility. Future consumer hardware must be powerful enough to run heavy world models and process sensory data entirely on the edge, independent of external servers. By breaking out of the screen, AI has turned digital intelligence into a direct lever for physical work.